Hello everyone. Today I would like to show you how to using Pearson to starting log on Pearson to read PowerPoint, watch videos, and apply StatQuench. I would like to share the screen right now. I'm going to do chapter 3. So first, I'll share my screen with you. So when you log on Pearson, you go to your own account. Then you click to Video and Resource Library. You click there, and it will appear a window having the following information. You see the chapters right here? There are a lot of chapters for you to click. Right now, I would like to focus on chapter 3, so I click chapter 3. And then what I need for the media type, we have a lot. So, however, my purpose, I would like to focus on reading PowerPoint and watch video, or maybe StatQuench. I click those and then I click Find Now. So after I click Find Now, then you will see the bottom right here. I'm having for video, the technology tutorial videos. So here you can watch how they run StatQuench for chapter 3 or more. And specifically, StatQuench will be right here, chapter 3, StatQuench. So this video will help us to see how they run. They're using data and material from chapter 3 and run StatQuench for us. In the PowerPoint, we are having section 3.1, 3.2, 3.3, 3.4, and 3.5. So what I'm doing right now, I would like to go over 3.1 or maybe 3.2. And you will see, because I do not want to record like too long, maybe maximum is 1 hour for you to can check back and forth my lectures. And we are having videos down here. You can see we have a lot of videos. However, for those who are not strong at algebra, you can spend time on integrated review videos right here. We have 2, 4, 6 of them. And for those who want to focus only on chapter 3 exercise, you start from chapter 3 review, videos, exercise 3.8, and so on. They have a lot for us to look at. So now let's jump to PowerPoint 3.1. For PowerPoint 3.1, what you notice is we've got objective for whole chapter 1. You will be focusing on numerical summaries of center and variation. And for specifically for 3.1 section, you learn about summaries for symmetric distribution. And in this 3.1, you will learn how to measure for center. Another word, they say balance points. Another word for this, what does it mean? It's mean. Mean represent for you to compute the center balance point when we are talking about symmetric distribution. So for distribution in chapter 3, you will learn symmetric distribution and you will learn skew distribution. For this case, to measure the center for symmetric distribution, you will find mean. What is mean? Is the average, right? And you will learn how to measure the horizontal spread. The horizontal spread is mean you measure on the side. How much the data will spread out. And in order to compute for symmetric distribution, people usually apply we call standard deviations. The standard deviations abbreviate for this term is small s. S like Sam. Okay, so now let's start. So appropriate measure. So let's recall when dealing with numerical data. You know numerical data, right? We got two types of data, right? Numerical data and categorical data. So for this case, so when you're dealing with numerical data, you need to describe the distribution using three characteristics below: shape, center, and spread. For numerical data, the shape can, of course, for the shape, we're talking about symmetric, which is the left and the right side roughly kind of the same, right? And the middle part will be all the way go to the raise to the top, like raise higher. For skew, you got two types of skew: skew to the left and skew to the right. What skew to the left look like, you can type on Google and search for it, or I can annotate here for you to look. Skew left look like this. The shape, they got like less data on the left, but more data on the right, because skew left. And skew to the right will be the opposite. They have more data to the right and then less data to the left. Okay, so the first one skew left, the second one skew right. And for the type, the center we call the balance points, or general we call typical value, because right here we're talking about two types of distribution: symmetric and skew. I do not say right here for the name, specific name apply for symmetric distribution. You call right here the mean for symmetric distribution. But for skew distribution, they call the center become median. Median, what is median? You learn from chapter 2 is median will be the central value of the order set from low to high. That data set have to be ordered from low to high, right? For the spread, they're talking about the horizontal variability. So right here for symmetric, for this section 3.1, you learn the spread for symmetric distribution will be small s, which is the standard way. Let me see here. The standard deviation, the sample standard deviation will be small s, abbreviates as S like Sam. So here, right here, they said in all chapter 3, you got 5 sections. You will learn specific ways to describe the center and the spread of the distribution. So you will learn a lot at the end of this chapters. You will understand, is it like, can I apply mean for skew? Yes, the answer will be yes. Can I finding standard deviations for skew? The answer will be no. So you will learn that for later sections, okay? So keep that in mind or write somewhere on your notes. Okay, so let me move on. So let's talk about mean. So right here, we are having the following picture, like a scale. You look at here, this scale is represented for symmetric. The left side and the right side will be roughly equal, right? But the middle part right here will be a bit up here like this. So can be thought as the balancing point of the distribution. That's the mean. How do you compute the mean? You compute the mean by adding all the given data together and divided by the number of the data. You will get the average. So, what next? The mean right here is giving us the definitions. The mean, in other words, the mean apply for symmetric distribution only. So, this dot plot shows the distribution of ACT scores for a sample of stat students. And this we call dot plot graph display. Each dot represents for one student. And the number down here represents for the score of the students they got. So one student have 18 score, one student got 19, and how many got 20? Count 1, 2, 3, 4, 5, 6. 6 students got 20 score on their ACT. For symmetric distributions, the mean is the good presentation of the typical of the data. So right here, you look at here, see the red triangle right here? Represent for the typical value of this data set. So this data set, you look, when you draw, it's roughly symmetric. It's not perfectly symmetric. However, even though it's roughly symmetric, you can apply mean to figure out the typical value for the whole data set. In this case, with this data, the typical value that is falling right here is like about 24.5 or something, 24.5, 24.6. So this represent for majority of the student, they take ACT, they having around 24.6, the score, their score will be around 24.6. For this distribution, so let's check it out, the mean for the student distribution. Will it appropriate to do it? You look at the data right here talking about salaries. We are having many people. Let's see how many family got around 400. Okay, 400 family, maybe they said 400 family, they gaining about how many? So the bottom right here, they're talking about salary. 1,000, 2, 4, 5,000, 10,000, 15,000, 20 million. I'm sorry, million, not thousand. Million, 5 million, 10 million, 15 million, 20 million, 25, and so on. So this we call histogram. See, histogram. Some histogram, they don't have to be connected, but majority of the histogram have to be connected. And from the width, the class width from here to here, we call class width. And you look at over here on the right side, here's empty. It means the data is not falling in within this bin. But however, you notice the leftover, the very outside piece right here, we call this is outlier. Maybe this box and that box we can call outliers too. Why? The reason is this distribution is skewed to the right. If they skew, they have a lot of outliers. If they are symmetric, mostly they don't have outliers. Outliers will be the bad things because it will screw up this distribution. You don't accurately estimate the typical value or other data, general data for the whole distribution. So that is why you will learn later. How do you find outliers? And I believe we did talk about this in chapter 2 too. Chapter 2, they're talking about box plot a bit, right? Hopefully later you learn more in this section or this chapter 3. And the red triangle right here, estimating the typical value will falling is in here. If they're using the mean, it's falling in right here. And when you look at overall this graph, you notice, I notice a lot of family, they having like about how many millions right here? It's maybe 1 million. Majority of them got 1 million, and more of them have 2 million, and so on. So if they're using a mean for skew distribution, it doesn't help. It doesn't help them to figure out accurately what is a typical value for this skew distribution. So let's read over right here. This distribution shows the salaries of professional baseball players in 2010. They're asking question. Do you think the mean is a good representation of this typical baseball salary for that year? I just explained to you, right? So it's not good. The mean will be not good when we apply into any skew distributions. So using the mean to describe typical value. First, the mean represents the typical value in a set of data when the data is roughly symmetric. For skew distribution, the mean is not a good estimate of a typical value. That's a conclusion. So how do we computing the mean? Like I said to you, you add all the data value given, and then you divide it by the number of the numbers. Which is, for example, I have 5 data. I'm going to add 5 data together, and then I divide it by 5. But the data can be decimal number or whole number or fraction or whatever. It can be huge, right? It can be like, if you're talking about the baseball player, they're making money like 1 million, 2 million, 3 million, stuff like that. You add all million together, but you still divide it by 5 only. You will get an average. So that is how you compute the average, the mean for symmetric distribution. Here is another example for the mean. So suppose that the sample of prices for 1 gallon of the regular gas at 10 different gas stations in a neighborhood in Austin, Texas, is taken on one fall day in 2013. So we need to find and interpret the mean. So we're having $3.19, $3.09, $3.09 for the third station, and so on. So now we check it out, the dot plot. So that's describing the story into the dot plot like this. See here? To you, this is skew or this is roughly symmetric? Yes, it is roughly symmetric. So, because it's roughly symmetric, you can apply mean to find it. And remember, for the symmetric, for any measurement for symmetric, you can apply that to find skew. I'm sorry, I said the opposite. Every way to measure the skew, you can apply that to find the value, typical value, and the spread for symmetric. Okay, that's more correct. Let's come back to the example that we are talking about, the gas station. So here is how you find the mean. In the sample, the notation for the mean is X bar. X bar here, we have another name, we call sample mean. You see that they add all of the data given, they divide it by 10 because we have 10 stations, 10 gas stations. You got the value is roughly about 3.02. This is the roughly general stand for like they estimating most of the gas station in Texas, in Austin, Texas will be around $3.02. So let's interpret that. I just interpret that on my own words. And here's how I interpret this. The typical price of 1 gallon of gas at this gas stations in Austin, Texas was $3.02 on this particular day in 2013. When I compute, then you will see the typical value will be stayed right here. If you are lazy, so right here we have a couple of slides for us to compute. Actually, when you are having TI-84 calculators, when you follow these steps, it not only give you the mean, it gives you a lot more. It gives you standard deviation, it gives you variance, it's gonna give you median, and a lot more. Okay, so right here, even though they just saying like this, but when you put your data on the TI-84, you will see a lot more. So let's talk about the measuring the spread. The spread is what? You learning about the data. So each data, they are the differences between each data, we call the spread. And how each of the individual data, they are a part of the mean. That is the spread. Or another word people call that is the standard, the sample standard deviations, S. And we are having, so let's recall, the variability in a distribution can be measured by the horizontal spread. Why do we care? Because we need to know if most of the data is near the center or far from the center. Okay, more data go close to the center is better because you can estimate the exact more exactly. If the data spread away from the center more, it's telling you it's kind of, I cannot estimate the future. I cannot estimate what will happen next. But if your data close to the center, then you can. So right here, however, assigning a number to a horizontal spread is not straightforward. This, okay, so this is not really tell us anything. However, you need to know that the more data close to the center, the better. So measuring the spread, here's the following example. Look at these two pictures. They are talking about Provo in Utah State and San Francisco City in California State. They're talking about the degree, the blue one and the yellow one. So look at this. Again, this is, of course, is histogram. To you, to me, I do not know how you feel, but to me, these two are roughly symmetric because if they skew, then you will see more data will be to the left more, like more data to the left or more data to the right. So right here is kind of 60%. It's still considered roughly symmetric. However, compare the spread of these two pictures. You notice a lot of data spreading out from here to all the way to here. They spread more compared to the yellow picture here. We're talking about San Francisco. San Francisco looks like more data surrounding the typical value, and this is more a bit spread out, right? However, compared to the blue one and the yellow one, the blue one more spread out. So I can tell the sample standard deviation of Provo, Utah, larger than San Francisco City. Okay, so here is the solution. So what I just interpret that, and here is they have more details. So both distribution roughly the same. Yes, kind of. The shape, they are roughly symmetric. The center, they roughly the same, 167, 165. The spread in both distributions, however, is very different. Like I told you, Provo, which is the blue graph, they're more spread out. The data is more further from the center. San Francisco is like close to the center. So on the test, actually, I'm not gonna tell you analyze this. Analyze this is maybe on homework. Maybe you look at the graph and tell like this, but on your test, you will compute sample standard deviations. So measure spread standard deviations. Standard deviation, what is it actually? Standard deviation here, you got two symbols. If you're talking about a small group, the standard deviation will be represent small s. Let's see, annotate this. Be small s. This is sample standard deviations. And we have another notation for standard deviation is sigma. Sigma here represent for population standard deviations. Small s here represent for sample standard deviations. They function the same, but s here can estimating sigma. Okay, it's like x bar can estimating the entire population mu. Standard deviation is what? Actually, standard deviation is just a number. We have to compute that. All the technology will compute it. A number that measures how far away the typical observation is from the mean. For most distribution, the majority of the data is within one standard deviation of the mean. So we think of the standard deviation as a typical distance of the observations from the mean, right? So here is a good slide for you to understand standard deviations. So here's the example. Let me erase it. The mark right here first. So the graph below, they're talking about what? They're talking about micrograms per cubic meters. They're talking about the air, right? So let's take a minute, read over this. You read on your own, please. Okay? So let's analyze this. Let's answer the following question. The first question, let's find the level of the particulate matters one standard deviation above the mean and one standard deviation below the mean. You know what does it mean? What does it mean, one standard deviations? 2 standard deviation and 3 standard deviations. So this relate to we call empirical rules. In the future, maybe next section you will learn this, but here let's simply talk about one standard deviation only. Number 2 question is, keeping in mind the EPA say that the level over 15 micrograms per cubic meters are unsafe. Should be less. If the level less than 15, then it's good. Or maybe equal. So what can we conclude about the air quality of most cities in this sample? So number 1, if you want to find the level, one standard deviation away from the mean and one standard below the mean, first what do? You have to figure out what is the mean and what is the standard deviation s. So those two data you have to point out from the original story. Go back to original story. So let's scan over this. They say right here the mean particulate matter is about 10.7. micrograms per cubic meters. And the standard deviation they given to us is 2.6 micrograms per cubic meter. So they're asking us to find a level, one standard deviation above the mean and one standard deviation below the mean. So this is how you're going to do it. You want to add or subtract that standard deviations. So here they got the mean, they add that 2.6. This 2.6 represents for one standard deviations. You add that, you got this level. And you subtract that. So this 8.1 is a value below the mean. 13.3 will be a value above the mean. One standard deviation above the mean. 8.1 is one standard deviation below the mean. So you can see the range from here to here is okay. It's less than 15, so it's okay. The air quality is safe enough for for most of the city, right? And again, this formula is important to you, but it's very complicated. So this good for less data, but it's complicated for a lot of data. It takes a long time for you to compute by hands. So I recommend that you can use StatCrunch or you can use TI-84. It's very simple. There's slide for you to follow how to compute that by using TI-84 or StatCrunch later. And please watch more video, or you can go to YouTube on your own to type in how to find standard deviation using StatCrunch or how to find standard deviation using TI-84, 83 if you don't understand when you read the slide, okay? So we have the following example. Again, they come back with the gas station. And in order to compute the spread between data with the mean, they have to do a long process by hands. But in this class, because in this class, we do mostly online, you learn online, so I don't expect you to compute by hands. But you at least look at how they do by hands right here. They got a table like this. And then in order to compute that, first thing you have to find the mean. Second, you have to take each individual x, you take away the mean. When you got that value, you will square that value. When you're done squaring that value, you're going to add all of that value together and divide it by n minus 1. In this case, we have 10 gas stations, you divide it by 1. You minus 1, you got 9. Don't forget to square root that to get the sample standard deviation x. Finally, you are having about 0.0855. It means roughly about 9 cents. The differences between each data compared to the mean is about 9 cents. So therefore, we know that the mean is this, the standard deviation is about this. What does it mean? At most of this gas station, the price of a gallon of the gas is within 9 cents of 3.02. So this is the mean, right? So most gas station, so the value will be between 0 to 9 cents of the $3.02. That is how you interpret the standard deviations. And later on, you will do the same thing. This is the way how you run StatCrunch. How to run TI-84. And for StatCrunch, very simple. So let me walk you through StatCrunch right now to see how you can compute it on StatCrunch. It's very simple anyway. Hopefully it don't take a lot of time. So I go to StatCrunch. Let's say StatCrunch for chapter 3. So we are having some data set that I already have it. So let's do air quality. So let me do the data. We are having the following right here. We don't care applets. We don't applets actually it's just like a tool for you to it's kind of similar to like graph and stat right here. But if you got more practice, experiment back and forth, you can check it out by yourself. So right here, I'm trying to find how they can find the sample standard deviations. Go to stat, summary stat, or calculators. If a calculator, let's see what do they have? Chi-square, exponential, gamma, geometric, how about geometric? Okay, you don't do this right now. For summary stat, got correlation, row, covariance, group mean data. Let's go back to that later. The table, you don't do table right here. Z-stat. Okay, so let's do Z-stat. There we have a more right here. But Z-stat is another word for Z-stat is Z-score or Z-value. Z-score or Z-value represent for a number of the sample standard deviation away from the mean. Kind of similar to sample standard deviation though. But I will go back to here to compute S. So let's move on to here. Let's see what happened. For t-stat is represent for the critical values as same as z-stat. However, t-stat represent for something related to degree of freedom, which is you not learn now. Proportion stat. So this is talking about fraction stat. You not learn this right now, but you will learn later. Variance stat. So variance stat is another way that you are computing the spread of the data. But variance, you have to do square root to figure out the sample standard deviations. Regression will be chapter 4. You will learn regression in chapter 4. ANOVA will be I think chapter 11, chapter 12, but we're not gonna get to here. Goodness of fit. Goodness of fit will be in chapter 4 sometime, or maybe chapter 10. Okay, so let's go back to Z-stat. Let's try it. Oh, we'll go back again. Stat, Z-stat, one sample with summary. Sample mean, let's say, right here we are computing the gas station, right? So let's try 0, 0, 2. Okay. Standard deviations. So roughly about, we did know this value already, but right here I think I got the wrong place. Let's go back. So it looks like stat quants, they don't let you compute sample standard deviations. Mean, oh right here. This low bound. What is the lowest value? Back to the PowerPoint. The lowest value that we are having. So what I'm gonna do, I will open StatQuants. I will type in my data or copy and paste my data. We did talking about the gas station, so I try to paste it here. Hold on. Go back. Ensure to delete this column. Let me see. You can rename right here. This is the value, right? Value for each gallon, at each gas station. And then I would like to, let me see if I can paste right here. So actually I have to type in, but it takes time, so I don't type in. You can type in on your own and do stat quants that I show you right here. You're gonna run you run stat quants right there, right? And then you go to, let me see, where did I just go to? I go to stat. Okay, I think I lost that. I just saw it, but where is it now? Okay, go to applets. Go to applets and go to mean standard deviation. You type in the data right here, this column. I type it in 10 gas station right here, and then you run it, compute, and you got it. So I'm doing by hand on your study guide. I have this doing by hands. I add all of it. I'm using another method. I take the absolute value. So I take each data X gas station. I minus the mean. I think I did wrong right here. So you can correct that. And then, okay, it looks like I have to recompute that. It's roughly, of course, is the standard deviation is around 0.085. Right, so I will make a change right here, and you can do the change right here for me too. You change to 3.02, okay, 3.02 for all. All right, so that's how you got it, using StatCrunch or doing by hands like I do, and that is how you have it. So I'm finished 3.1, and good luck.